My name is Wilmer Hjulström, and today I will present my thesis, Guidelines for FEA Methods for Bolted Joints under Random Vibration Fatigue. Bolted joints are simple components that can be found in almost any type of mechanical structure. Anywhere from bridges to aircrafts, submarines and cars, you will find bolted joints. But their behavior is not simple when they are subjected to vibrations. When they are subjected to random vibrations, they can experience a wide range of phenomena, including slipping, bolt bending, and fatigue failure. The motivation of this thesis is the conflict between trustworthy fatigue prediction and computational efficiency. This work was carried out in collaboration with Combitech, and in industrial FEA, engineers often work with large assemblies containing dozens or even hundreds of bolted joints. Modeling every single bolted joint as a fully detailed threaded model would be extremely computationally expensive when it comes to preparing, meshing, and solving. Therefore, engineers tend to use simplified models, but these simplifications, the question is not whether simplifications are useful or not. The difficult question is when one specific simplification is acceptable. The main research question of this thesis is: how can guidelines for finite element modeling of bolted joints be defined to optimize accuracy per cost with respect to fatigue analysis and phenomena caused by random vibration? My hypothesis is that such guidelines can be formulated based on three components. First is the relevant physical phenomena, second is the fatigue accuracy, and last is the computational cost. The question that the thesis asks is not which of these bolt representations that is the best. It asks how can we choose the cheapest representation that still answers the engineering question with sufficient confidence. Deliverables. The thesis has three main contributions. First one is the phenomenon method matrix that connects different phenomena to the analysis type and bolt representation that can capture these phenomena. Second deliverable is the decision flowchart that sort of works as a map that walks the engineer based on a set of questions to a recommended analysis type and bolt representation. The last contribution is a comparative computational benchmark that aims to quantitatively find how accuracy and cost changes with fidelity or bolt representation. Before going into the finite element models, I will briefly explain the analysis chain that is used. First is the input. Two different acceleration PhDs are used as an input. These describe the vibrational environment that the bolts will be subjected to under an experimental physical fatigue test or vibration test. The top one is the NASA STD-7001D workmanship. And this describes the vibrational environment that electronics in the cockpit of a spacecraft needs to survive to pass a test. The other PhD describes the MIL STD-810G T43A, and it describes the vibrational environment that cargo in a T43A aircraft experiences. The actual analysis, or the fatigue pipeline, starts with a nonlinear static analysis. That is where we apply the preload. Basically, we are tightening the bolt. When this is performed, we freeze the contact state and perform a linear perturbation analysis, where we compute the dynamic response. From the dynamic response, we can extract the stress PSD tensor. Using this, we can then use the Siegelman method to transform this tensor into a scalar Siegelman von Mises equivalent stress PSD. After that, we use Goodman mean stress correction, and we use the Dirichlet method to compute the fatigue damage rate. The key point here is that this pipeline, this analysis, is kept constant across all representations, so any differences are at least not from changing the method itself. I've already mentioned that bolted joints can experience a wide range of phenomena. This thesis addresses 8 different phenomena, and all of these 8 phenomena does not require the same type of analysis or same bolt representation. For example, if we know that we don't want any slip at all, then we can use a binary check analytically and compute just to check if the shear force exceeds the friction force or the friction capacity, and see if slipping is a risk at all. Other quantities or phenomena can be computed with a linear perturbation. This is the type of analysis that is performed in the benchmark. Some quantities that can be found with this type of analysis is stress PC, bolt bending, and fatigue around a preloaded state. Other phenomena, such as self-loosening or other thread-aware phenomena, requires nonlinear transient analysis. The key point from this slide is that the engineer should not start by asking, or should not just decide to use one type of analysis or one type of representation, but instead start by asking which phenomena will be design driving, which phenomena do I care about. No finite bolt model is good or bad in isolation. It is only appropriate or inappropriate dependent for a specific engineering question. Here, sort of in the same line as the last slide, we need to separate different phenomena for different analysis, and also different regions, because for global estimates, global responses, or clamped member response, a more simplified model may provide sufficient information, while if you're looking at the bolt itself in local regions, simplifications are generally not as useful as more detailed or high fidelity models. This is the reason why the thesis separates global or clamped member response from local bolt response. The benchmark that is used is a single bolt benchmark, and in order to make the experiment controlled, there is only one variable is changing. The mesh is kept constant, the excitation, the loading, the boundary conditions, everything is kept constant except the bolt representation itself. This benchmark does not claim to represent any type of bolted joint. For example, it does not include any multi-bolt patterns or complex production assemblies. These 4 bolts are the representations that I used in the benchmark. First one is the bonded surface representation, and this is the cheapest and the most simplified model. So it's cheap and it's simple, but it also removes the bolt body completely, and it also removes the slip degree of freedom. Next up is the C-bush, which is basically 6 independent linear springs. And this is also cheap, and this is very tunable, but this tunability is also a vulnerability because its accuracy is strongly dependent on the input from the engineer. Third representation is a beam model. Here we give the bolt a beam type behavior, and we can extract axial stress and bending behavior, but still we cannot solve any 3-dimensional stress concentrations. Last up is the threadless solid representation, and this one is used as the reference in the benchmark. It can compute 3-dimensional stress transfer and stress concentration in the underhead fillet, but still it does not have any threaded geometry. One thing to discuss is the use of this threadless solid as a reference, because it's not necessarily the most defensible model to use. More defensible would be to use an experimental test, a measured physical fatigue life. But this would also require, it would shift the scope of the thesis from being having FEA as the central subject to be more of designing the experiment, designing the specimen, having preload control, vibration testing, and experimental post-processing. This is out of scope for this thesis. Next up, another better or more defensible model would be a threaded model. And it would make total sense to use this. But under the linear perturbation approach, where we freeze all contact states, the threaded model would behave essentially the same as the threadless model. And therefore, I went with the threadless solid model. It's still more detailed than the simplified models, but it captures three-dimensional stress transfer, and it is compatible with the linear perturbation. 16 simulation cases was done. I already told you about the two inputs, the two acceleration PSDs, and the four models. The excitation was then put in two different directions, horizontal and vertical. These are not performed simultaneously, so it is two different directions times two different PCs times four models. This is 16 cases. Fatigue failure would happen in one of these three regions in a clamped, in a bolted joint. First region is the clamped member region, close to the hole. This is the only region that is identical across all four representations. So this is also the only region where the representations or the models can be compared directly. The other two regions are local bolt regions. And first of all, here I already mentioned that the C-bush and the bonded model has no physical body to extract stress from. Still, we got the beam and the solid. The beam provides finite stress response, but it cannot capture the stress concentrations. The solid can. Three main quantities was extracted from these regions. First, the stress PSD. Second, the RMS von Mises stress. And third, the Goodman-corrected Dirichlet fatigue life. In order to compare these models, these representations, a ranking index was constructed or introduced. It combines three different errors, and these are the minimum Dirichlet fatigue life, the relative error in maximum RMS von Mises stress, and the relative error in the 95th percentile RMS stress. This is then normalized so that a score of 100 means perfect agreement with the reference. The cost function is also a construction, and it involves the mean value of all clock time and CPU time, and this is also normalized so that a score of 100 means perfect agreement with the reference. Efficiency is defined as ranking index divided by cost, and the ranking index of more than one means that we get higher ranking index per unit cost than for the reference. Results. So this is the stress PSDs for the clamped members, the only region where we can compare every model directly. And I see now that this is pretty hard to see, but we got some dashed light blue lines here and a more thicker blue line. The light blue line is the beam model, and the thicker is the reference, the solid. And comparing these two only, we can see that the location of resonant peaks, it's more clear here perhaps, are very close. And this is also true for the stress amplitude. Looking at the lighter yellow line, that is the bonded model, it still agrees closely with the location of the resonant peaks, but the stress amplitude has a conservative bias. The C-bush model, the orange here, sits between the bonded and the beam. This conservatism is not necessarily reliable or controlled, but it is something that was observed. Looking into the local regions, once again, we cannot extract any stress from the C-bush or the bonded model when it comes to local regions, but we can from beam and from the solid. And since the beam cannot extract any or capture any stress concentrations, it also gives a much lower level of stress and therefore is non-conservative when it comes to fatigue life. The interpretation of these two last slides is that the beam model is preferred for this benchmark when it comes to clamped member fatigue, but when it comes to local bolt fatigue, a three-dimensional representation is required or preferred. I mentioned in the analysis that I used the Dirichlet method to compute the fatigue life or fatigue damage rate. But this is not the only method there is. There is also one other common method, is the Steinberg method. And in order to see whether the ranking is an artifact or dependent on the method, I decided to compare these two, and the answer is that it is not dependent, because at least these two methods agree very closely for critical nodes that has shorter lives, the design driving nodes. The cost results shows that the bonded and the Bush model are much cheaper than the beam or the solid. And they are also more efficient in this definition of the efficiency. But I don't think that this sort of efficiency is something that should be used to validate a choice of models. Because even though these are efficient and looking just at the front, at the parietal front, the beam would not be considered. But the beam can provide much more information than these models. And that should be something that is more decision driving than anything else. The first deliverable I also mentioned briefly is the phenomenon method matrix. And this is meant to connect a phenomenon to methods and representations. For example, if the engineer needs to see slipping as a binary check, the engineer can look here and see that an analytical approach with a bonded model is good enough, can be good enough. If the engineer wants to see underhead fillet stress, then it shows that we need a threadless solid. Some other phenomena, such as self-loosening, needs a nonlinear transient analysis and a threaded solid. This matrix helps the engineer to not under-model or over-model the representation, and it also sort of gives a feeling that we don't need to put cost here. We can put the cost somewhere else, or the work. Next, a deliverable is the decision flow chart, the map, and this walks the engineer based on a set of questions into a recommended bolt representation and analysis type. For example, if once again, same example as in the matrix, if the question regards slip risk, then it will point towards an analytical check. If the question regards clamped member fatigue, then it will point towards a linear perturbation, and based on the benchmark, it will also recommend using a B model. These deliverables are not meant to be a substitute for engineering judgment. It is only a way to be more transparent in the decisions and make any choices or decisions more repeatable and easier to justify. Some important limitations are these four. First of all, the single bolt benchmark cannot represent any type of joint, so the model and the ranking index and the other deliverables should be revalidated for multiple patterns or complex assemblies. The threadless numerical reference is not measured physical fatigue life, and it should also be compared to some sort of experiment or test. The linear perturbation removes many physical phenomena. any nonlinearity is not captured. And the single axis excitation is also a limitation. Multi-axial excitation might give different answers, different results or conclusions. Main conclusions is that there is no single best representation. It is case dependent and should be looked into for every single case. For clamped member fatigue, in this benchmark, the 1D beam is the preferred choice. For local bolt fatigue, three-dimensional solid is required. And for thread level phenomena, a thread aware and a transient analysis is needed. That's it.